Hello everyone, Mr. Fawcett here, and we are back with another geometry lesson. Today we're going to take a little break from talking about parallel lines and transversals, and we're going to shift into a discussion of perpendicular lines. You may have talked about perpendicular lines in Algebra 1 and what the slopes of perpendicular lines were. Today we're going to focus more on the angles formed by perpendicular lines, and then use that information to not only do some proofs, but solve some diagram problems as well. Before we get to any perpendicular line things, you are first going to complete this do now. 3 questions. You have an inequality to solve, an equation, and a system of equations. So pause the video, take 3 or 4 minutes to work through these, and then come back and see how you did. All right, so we're going to start off with the inequality. Good news is that for the most part, penmanship wasn't very good. Good news is, for the most part, these inverse operations work the same way they do for equations. So I'm going to add 5 to both sides. I get negative x is less than or equal to 13. And then I'm just going to divide by negative 1. Now, the one difference between equations and inequalities is that if you multiply or divide by a negative number, you have to switch the inequality sign. So if I divide by negative 1, I'm going to get x is greater than or equal to negative 13 for my answer here. All right, let's move on to our equation. I'm going to subtract 15 from both sides. I'm not going to write that out, but we have 5x is equal to 75. And if I divide both sides by 5, I get x is equal to 15. Now we come to number 3, which is our system of equations. Fortunately, one of our equations is just a single variable equation. So we can just go ahead and solve the top one right away, figure out what our value for y is. So I'm going to divide both sides by 6, and I'm going to get y is equal to 15. I can take this value for 15 and substitute it into my second equation. So instead of 8y, I get 8 times 15 minus 3x is equal to 90. I can simplify. 8 times 15 is 120. Not sure why my finger's catching on the screen so much in this video. 120 minus 3x is equal to 90. I'm going to subtract 120 from both sides, so I get negative 3x is equal to negative 30. Then I'm going to divide by negative 3, and I get x is equal to positive 10. Negative 30 divided by negative 3 will give me a positive 10. So for this system of equations, I have a solution for x and a solution for y. We didn't have to do any elimination or a different type of substitution here because the first equation just has single variable. So easy to solve that one and then substitute into our second equation. All right, let's start talking about perpendicular lines and segments. All right, so here's a little intro for you. You have 3 diagrams here, but all with line AB. They just don't have the arrows on them. You can treat them as a line, and a point C somewhere near that line. So what you're going to do is draw the shortest segment possible from C to the line AB. So just for example, you have C up here. You can think about, is that the shortest segment? Is that the shortest segment to line AB? Or is there another segment I could draw? Maybe one of these is the shortest. You just need to figure out what the shortest one is. And then you're going to come over to the second diagram and the third diagram. Once you draw the shortest segment from point C to line AB, and again, you're just trying to come up with one segment for all of these diagrams. Maybe you want to sketch a couple to see what one the shortest is, but then you eventually just want to have one. Once you do that, you're going to answer the question down below. It says, what do you notice about all the segments that you drew? There should be some common theme throughout all of them. All right, so pause the video, attempt that, and then come back and listen to the discussion. Okay, so if I draw the shortest segment here, I'm going to come straight down. Over here, I'm going to come across like this, and over here I'm going to go straight across to my right. And again, maybe because of the title of this lesson or you've studied this before, all of these segments are perpendicular, right? They all seem to form right angles with line AB. So they are all perpendicular to line AB. All right, let's move on. We're going to keep that in mind though. The shortest distance from a point to a line will be the perpendicular segment, right? Actually, I'm going to stay here for a second. Notice that if you drew any other segment, right, it doesn't matter whether you go to the left or to the right of that pink line, it's always going to be longer than the perpendicular segment. And maybe, depending on how far you got in your middle school geometry section, something pops out at you here, right? You may notice that, okay, we have a right triangle in all three of these diagrams. And the perpendicular segment is one of the legs of the right triangle, right? We have a leg here, and a hypotenuse. But each perpendicular segment is a leg, right? The perpendicular segment is never the hypotenuse. So if the perpendicular segment is never the hypotenuse, well, it's never going to be the longest side, right? Because any other side that you could draw here ends up being a hypotenuse. If we look at the first diagram, let's say I erase the green segment. I'll make another one. It doesn't matter if I come in a little bit closer, this still becomes a hypotenuse, right? And I can go to the left side. I can go over here. And even though, now that's a little confusing, but it still becomes the hypotenuse. And this side becomes the leg. It stays the leg. So because that perpendicular segment is a leg, and every other segment that you could draw from C to line AB would be a hypotenuse, that's another way to show you or to prove that the perpendicular segment will always be the shortest, right? Because it's always going to be shorter than the hypotenuse, which is what every other segment would be that you could draw. All right, now we'll move on. So perpendicular lines. The shortest segment from a point to a line will always be, I'm sure you can guess, perpendicular to the line. So the shortest segment from a point to a line will always be perpendicular to the line. All other segments will be longer than the perpendicular segment. And then let's look at a couple of examples where we're asked to solve for a variable. I would encourage you to try to answer number one, both the question and then part A down below on your own. If you're a little confused, again, just think through it for a couple minutes and then you can come back and listen to the discussion. But again, always best to try to think about these before you just hear the solutions. So number one says, which segment in the diagram is the shortest? AP, BP, or CP? Well, again, all three of those segments, right? I'll draw AP in purple, PB in red, and PC in orange. Well, the only one that's perpendicular is PB, right? So, or BP, you could call it. So again, we just talked about, we did a little visual on the first page. We just looked at this statement right here. The perpendicular segment is always going to be the shortest one. So BP is the shortest because it is the perpendicular one. We don't have to do any measuring. We can just make that statement based off of what we know about perpendicular segments. Well, now we're asked to write an inequality to solve or for the value of x. So if we know that the purple segment has to be longer than the red segment, well, we could do x plus 3. If it has to be longer, that's going to mean greater than. It can't be equal to, right? Because if it was equal to, that segment would also be perpendicular, and it's not. So it has to just be greater than the value of the red segment or the length of the red segment, which is 5. And then if we solve, right, we're going to subtract 3 from both sides and get x is greater than or equal to 2. Again, this has to be an inequality because x doesn't have to be 3, which is greater than 2. It doesn't have to be 4. It could be any number greater than 2 because any number greater than 2 will give the purple segment a longer length than the red segment. And of course, you could just test numbers larger than 2 to make sure that that works, but it does. All right, let's look at number 2. Again, I encourage you to pause the video and attempt this problem on your own. It's similar to the one above. There's a little difference, but we're going to discuss that when we go through the solution. Okay, so question says, which segment is shorter, AB or AC? So AB is in red, AC is in purple. Well, just like the last one, AB, let's make that different color, not purple. AB is the shortest because it is, again, the perpendicular one. And now we're asked to write and solve an inequality for the value of x. So this time our x is on the perpendicular segment, so we have x minus 5. We know that the red segment has to be shorter than the purple segment, right? Because the red segment is the perpendicular one. So less than 12. If I solve this, I add 5 to both sides, I get x is less than 17. So think about this. Does this make sense? If x is any number less than 17, will the red segment always be shorter than the purple? Well, if x was 15, then the red segment would be 10. 15 minus 5 is 10, which is shorter than 12, so that works. Now, we're not quite done with this problem. What I would encourage you to do is think about, does every number less than 17 make sense for this problem? So pause the video, think about that question. Does every number less than 17 make sense for this problem? Okay, so you may have tested, maybe you tested all the numbers less than 17 that you could think of. Of course, there's an infinite amount of numbers less than 17, so we'd be here till eternity if we tried to test those. But maybe you tested only positive ones, right? Or maybe you tested numbers that were greater than 5, right? Because as soon as you let x equal 5, let's see what happens. If x is equal to 5, then segment AB is equal to 5 minus 5, which is equal to 0. And that doesn't really make much sense, right? How could something have a length of 0 unless it wasn't actually there at all, right? Well, what if x was equal to 4? Then we have AB is equal to 4 minus 5, which is equal to negative 1. Well, that certainly doesn't make sense, right? Because we can't have a segment with a negative length. If something exists, it's going to have a positive length, not a negative one. So this inequality we came up with over here wasn't actually the only one that we needed to come up with. We actually have to think about, what does the segment have to be greater than, right? The length of the segment can't be negative. It also can't be 0. So segment AB, the other inequality that we need to write, segment AB, or x, oops, I need my pen, x minus 5, that also has to be greater than 0. Otherwise, some solutions that are less than 17 aren't going to make much sense. So if we add 5 to both sides here, we have x also has to be greater than 5. This is called an AND inequality because our solutions have to fit both restraints. They have to be less than 17 and they have to be greater than 5. The other option would be an OR inequality. But here that doesn't work because it can't just fit one of these constraints, right? It has to fit both of them. So something to think about when you're given a problem like this, think about, is there another restraint that we have to come up with as far as an inequality goes? Sometimes there's only one, like the one above, when something has to be greater than a number. But when something has to be less than a number, then we have to worry about, well, if it's too much less, it's going to run into the negative numbers or a zero, which we can't have happen. So we have to set up that second inequality. All right, so those are a couple of examples of diagram problems. Let's now talk about some theorems. And we'll try to get through this video in one shot, maybe a little long, but well, we'll see. So we have three theorems here. Theorem number one. If two lines form a linear pair of congruent angles, then the lines are perpendicular. And you can also think, right, if we have a linear pair of congruent angles, they're going to have to be right angles. You can see that over here in the diagram, right? You have a linear pair of angles, and they are both congruent because they both have that single red arc. If that's true, then line L is going to be perpendicular to line M. The other thing I was saying, right, is if you have a linear pair, and you know that the angles are congruent, well, the angles have to add up to 180 for a linear pair, right? Because a linear pair of angles forms a straight line. So if they have to add up to 180, well, the only measurements that they can have if they're congruent are 90 degrees and 90 degrees, right? If they were both 70 and 70, then they wouldn't be a linear pair because they wouldn't add up to 180. So you can use either of these words to think about this theorem with. You can either say that if two lines form a linear pair of right angles, then the lines are perpendicular, or if two lines form a linear pair of congruent angles, then the lines are perpendicular. Theorem number two, if a transversal is perpendicular to one of the two parallel lines, then it is perpendicular to the other line. And this does have a special name. This is called the perpendicular transversal theorem. We won't use it too much throughout this entire course, but it will show up here and there. So if we come over here and look at the diagram, again, we see that line Q is perpendicular to line N. Well, if Q is perpendicular to line N, we know that those lines are parallel, which means corresponding angles are congruent, which means that purple angle I just drew in there is also a right angle. Again, because if we have parallel lines, then corresponding angles are congruent. And if that purple angle must also be a right angle, then Q and P also must be perpendicular. Again, if you need me to slow down, I would just rewind it. Rewind it and listen to that again. Pause, think through it while you're looking at the diagram to help you understand what these theorems are really talking about. The third one, if two coplanar lines are perpendicular to the same line, then they are parallel to each other. If two coplanar lines are perpendicular to the same line, so over here we see these two lines. We know that they're perpendicular to line T because they both form right angles when they intersect T. Well, again, this is kind of going the opposite way that the second theorem was going. So if we know that the corresponding angles are congruent, well, then we can say that the lines are parallel, right? This goes back to the converse of the corresponding angles postulate. If corresponding angles are congruent, then the lines are parallel. All right, theorems 1 and 3 don't have a special name. If we end up having to use those in a proof, we're just going to write out what the theorem says. Again, so only number 2 has a special name as that we can use for a shortcut. The other ones, we would just write out the entire thing if we want to use it. Let's go and look at a proof, though. I think we're going to prove the perpendicular transversal theorem. So we're going to prove theorem number 2. All right, it looks like I can squeeze everything on there. Okay, so like I said, we're going to prove the perpendicular transversal theorem. Now, because we're proving it, we're not going to use that anywhere in our proof, right? If we're trying to prove a theorem, we can't use the theorem in a proof that we're using to prove that that theorem's true. So in none of our reasons boxes should we say perpendicular transversal theorem. What I would encourage you to do is pause the video and see how many of these boxes you can fill in. I always encourage students to go in order and not to just skip around in a proof. If you're just skipping around, you're not really getting the full cohesive idea of what the proof is saying. Force yourself to sit there and really try to go in order. Even if you're like, ooh, I know what that next one is. Well, no, stop and try to make sure you get all of them in order first. All right, first one, that's an easy one. That is given. We are told that lines BC and DE are parallel and AB is perpendicular to BC. So what we have here is that we have two parallel lines and we have a transversal that's perpendicular to one of them. Then we're told that the measurement of angle ABC, so that's that angle right up here, is equal to 90 degrees. Well, if we know that AB is perpendicular to BC, perpendicular means that there's a 90-degree angle formed where the two lines intersect. So this would be definition of perpendicular. All right, moving on to the second one. We have angle ABC is congruent to BDE. So ABC is already the one up there in purple. BDE is down here. So we're told that they're congruent. Again, this goes back to the fact if we have parallel lines, corresponding angles are going to be congruent. And I'm going to type this one in here because it's a little bit of a long one. This is the corresponding angles postulate. Okay, if I know those angles are congruent, I know that they are equal in measurement due to definition of congruent angles. I'm just going to keep typing, actually. It's a bit easier. I have to write more than one word at a time. All right, if I know that they're both equal in measurement, well, up here, we already talked about angle ABC having a measurement of 90. So if I combine that with this statement right here, right, we can do some substitution, specifically transitive substitution. So here we have transitive property of equality, transitive POE. Again, substitution property of equality is an okay answer here. It's just not the best answer. It's not the most specific answer. And if we know that this angle down here is 90 degrees, well, that tells us that line A, B, and DE are perpendicular by the definition of perpendicular. I'm going to keep typing, actually, because that's much easier. So the definition of perpendicular is not something we've really used before in a proof. The other ones we have, but this one we haven't. So the definition of perpendicular can go two ways. If you know that an angle is 90 degrees, then you can use the definition of perpendicular to show that the lines are parallel. That is what we did down here at the end. Okay, so let's just talk through that one more time. The definition of perpendicular can be used to show that two lines are perpendicular if they form a 90-degree angle. You can also go the other way, right? You can say if two lines are perpendicular, then they will form a 90-degree angle by the definition of perpendicular. Okay, and if you want to say the definition of perpendicular lines, that's fine. I will allow you to just say the definition of perpendicular because we don't have perpendicular angles or perpendicular, other things aren't perpendicular other than lines or segments. So you can just say definition of perpendicular. All right, so those are the two instances where you may use the definition of perpendicular inside of your proofs. All right, I think I'm going to let me clear this. I'm going to let you do the other two proofs on your own, okay? We can discuss them at a later date, but work through those. And we're going to do one of these problems down below. So let's do number 4. It says find the value of both variables in the diagram below. So we have an x and a y. Well, let's think about what we know, right? We have two angles here. We have this angle right here, and we have this angle right here. I'm not going to say that they're congruent until we talk through why they may or may not be. So a couple things you could do. You could say, okay, those look like alternate interior angles, which is true, right? They're alternate interior angles. Because these lines are parallel, those angles have to be congruent, right? So if they're congruent, they got to have the same measurement. So you could set up an equation, and we could actually fix this now. We could make this, we could make these congruent because we've just talked through why they're congruent. But I could say 3y minus 2x is equal to 2x. I could add 2x to both sides to get 3y is oops, let's fix the x up there. After I add 2x to both sides, I get 3y is equal to 4x. But then I'm stuck because I have two variables and just one equation. So I'm stuck. I can't really go any further. So can we use anything else from the diagram? Is there any other equation we can set up? Well, notice that we have this right angle here, right? We have a right angle here, which means that's 90 degrees. So if you want to label that as 90 degrees, you can. What's the relationship between these two angles? Well, they're same side interior, right? If they're same side interior and the lines are parallel, they're going to have to add to 180. So I could say 90 plus 2x is equal to 180. I could solve. I subtract 90 from both sides. I get 2x is equal to 90. Divide by 2, I get x is equal to 45. Once I know that x is equal to 45, it can come back over here. I'm going to get 3y is equal to 4 times 45, which is 180. Divide both sides by 3, I get y is equal to 60. So again, we had to come up with two different equations from this diagram to make this work. There actually was another way that we could go about solving it. You could notice that these two angles right here, let me do that in different colors so it's a little bit easier to see. You could notice that these two angles, oops, need my pen, these two angles, there we go, were a linear pair, so you could add those together and get them to equal 90 as well. So that could have been one of your other equations also. Okay, we are going to stop the video there. I encourage you to work through the other problems in the video if you'd like. Otherwise, we will go through them at a later point during class. All right, that's Mr. Fawcett. I hope you enjoy the rest of your day. And as always, I will look forward to seeing you next time.